Welcome to Power Electronics Education Electronic Book, Lecture 1 Introduction. This lecture is presented by Dr. Firuzare. The contents of this lecture are: what is power electronics, power converters, power switches, power modules, and applications of power electronics. What is power electronics? Power electronics is power processing. It's an application of electronic circuits to control a power converter in order to change the input voltage or current magnitude and or frequency suitable for different loads. In a power electronic system, the flow of electric energy is controlled based on a load demand. The main aims in modern power electronic systems are to deliver the power with maximum efficiency, minimum cost and weight in an integrated circuit. Power electronics has a significant role in different industries when power processing is required, such as in computers, telecommunications, motor drives, cars, and alternative energy systems. So this is a simple block diagram of a power electronic system. Basically, power electronics can be split into a power and a controller or electronic circuit. The power circuit converts the input power and delivers it to the output. The electronic circuit or controller controls the converter by measuring the input and output voltage or current and compare with the reference in order to generate the signals for the power circuit. So that means the controller compares the output voltage or current compared with the reference, and then generate the signals at low voltage, low power. And then we can turn on and turn off the power switches in the converter to chop the high voltage or high current in order to generate the same signal, same voltage or current waveform in very high voltage, high power system. That means the power processing means a mapping from low voltage into high voltage. That means using signal processing we can synthesize any voltage or current waveform, and then we can generate the same signal in high voltage, high current. In general, circuit elements in most electrical systems are resistors, capacitors, magnetic elements, it can be either inductor or transformers, and transistors operate in switch mode or linear mode. So some of these components may be used in low or high power systems. In most electronic circuits in which efficiency is not the main concern, so circuit elements consist of resistors, capacitors, transistors operate in switch mode or linear mode, but normally we don't like to have magnetic elements like inductors or transformers because they are large in size and difficult to be integrated. So that's why the transistor may operate in linear or switch mode, and the reason is that the electronic circuit operates at low voltage, low power. In power converters, efficiency is the main concern. That means power circuits consist of capacitors, magnetic elements like inductors or transformers, and transistors operate in switch mode. So in this case, we don't like to have any lossy components like resistors or linear mode device, because you're talking about high power, high current, and these lossy components increase the losses, decrease the efficiency, and cause the thermal problems. A power electronic system may process input power and deliver it to a load based on these following converters. So when we are talking about input source, it can be either AC or DC. And when we can say that we can change the power into AC or DC, so that means we have either DC or AC at the output. So that brings four different combinations. The first one is DC-DC converter. For different applications, we can control output magnitude. For example, if the input voltage is pretty low coming from a battery, we can boost the voltage. We can provide more voltage for different applications. Or if the input voltage is pretty high, because coming from, for example, a rectifier, and if we need low voltage for electronic system, we can reduce the voltage magnitude. The next type is AC-DC converter. So in this case, we convert the AC into DC. This is basically a diode rectifier. That means if we have AC voltage, using diode rectifier, we can get DC. With the filter, basically we get this type of voltage. So that means changing from AC to DC, there are different applications, because we can get DC voltage here unregulated, and using this converter, DC-DC that I described at the beginning, we can get different DC voltage at different level. The next type is DC-AC converter, which is basically an inverter. That means if you have a DC voltage coming from battery or any rectifier, then we can change the AC. In this case, we can change the output frequency and magnitude, or we can create different AC signal with different frequency and different magnitude. So how we can get the DC? The DC voltage can come from battery or can come from this type of regulator that I described previously. So this type of converter is not very common in industry, but normally we can use it for some special AC drive system for some industrial applications, or in very high power we can use cycle converters or matrix converters for some drive applications. Different applications have different load requirements which need special consideration in topology and control circuits. For example, in a DC power supply, if we have to generate DC voltage, so normally we need to get regulated voltage at 5 volts or 12 volts, depends on application. So that means the output voltage is almost constant. Or in another application, for example, in a DC motor drive, the output voltage should be adjustable, because for variable speed, we need to change the DC voltage. So the output voltage should be adjustable, because otherwise we cannot control the speed. In an AC power system, when the output voltage should be AC, that means we should be able to control the frequency and magnitude. So in this case, depends on an application. If it's an AC power system application, normally the frequency is constant, so we need to control the magnitude. Or in an AC motor drive, we should be able to control the frequency and magnitude in order to control the speed. The controller is an important part of the system to control and regulate output voltage and current, and also to protect the system in a harsh situation such as overcurrent, overvoltage, and or over temperature. So what's happened, the controller can measure output current or output voltage, and then it can also compare that one with the reference signal. The reference signal can be also current or voltage, and then based on this one it can generate the control signal. It can generate pulse pattern suitable for this converter, which can turn on and turn off the power switches to provide desired output voltage. When we design a power converter, it's quite important to understand the converter modes of operation. That means we have to know the output current and voltage. For example, if you look at this power converter, in some applications we need to have positive voltage or negative voltage, and sometimes the output current should be either positive or negative. So in this case, the system can operate either in this mode, that means output current is positive, output voltage is positive, or in this mode, whereas the output current is positive, output voltage is negative, or in this mode, when the output voltage and current both are negative, or in this mode, output voltage is positive, output current is negative. So basically the converter topology will be different when it operates in 1, 2 or 4 quadrants. That means the power switches in this power converter should be determined based on this power flow. This is an unidirectional power flow in which the power is controlled and processed from the input side, and transferred to the output. So what's happened, because the system operates in 2 modes, this quadrant and this quadrant, that means the output voltage should be positive while the output current is positive. So that means the output voltage is positive, and in this case the current should be positive. Or if the output voltage is negative, the output current should be negative. That means in this case the output current is in this direction and the voltage is also negative. So when we know these modes of operation, then we can design the power converter to be able to deliver positive negative current and provide positive negative voltage. So this is a bidirectional power flow in which the power can be controlled and processed from the input side and transferred to the output side, or vice versa. That means sometimes from output side into the input side. So in this case, as you can see, the system operates in 4 quadrants. In these 4 quadrants, that means the output voltage can be either positive, while the current can be positive or negative, or the output voltage can be negative, while the output current can be either positive or negative. So the key point is that the power converter should be able to actually transfer this power from input to output or from output to input. So in a power electronic system, line and EMI filters are important sections of the system as well. That means we need to have a filter on the input side and also on the output side. Depends on some applications. Sometimes we don't need to have filter, especially in AC motor drive, but for some applications, especially for power system application or in UPS, uninterruptible power supply, we need to have output filter. But input filter is also important because we should be able to control the low frequency and high frequency noise. In modern power converters, due to advances in semiconductor switches, converters can be classified according to low and high frequency switching devices. So the first type is low or line frequency converters, because sometimes we actually switch at line frequency, which can be either 50 or 60 Hertz. Normally these type of converters are control or uncontrolled rectifiers. The next one is high frequency converters based on hard or soft switching, in which controllable switches like MOSFET, IGBT in the converters are almost turned on and off at frequency higher than the line frequency. So let's start with uncontrolled line frequency converter based on power diodes. This is a single phase. We can change the AC voltage into DC, we can rectify the voltage. If we have a capacitor across the output, we can get better voltage, similar like this. But still this voltage is not regulated. We need to have another converter to actually control the output voltage. This type, if you can see, the switching happens at line frequency, so that's why if the frequency of the grid is 50 or 60 Hertz, so basically the switching happens at this frequency. But when we have three-phase system with 120-degree phase shift between the phases, so almost we can get regulated voltage, but depends on the topology. If we have half a control or full control, basically we can get a better voltage waveform compared to single phase, but again the switching actually happens at line frequency. This is control line frequency converter based on thyristors or SCR. That means again we can change the AC voltage into DC voltage, but the point is that we can actually change the firing angle. That means we can actually decide when to switch the thyristor, and that's why we can control the output voltage compared to diode rectifier. But still I have to say that the system actually operates at low frequency. That means if the grid voltage is at 50 or 60 Hertz, again the switching happens at this frequency. Or in a three-phase system, again we do the same. We can actually control the output voltage by changing the firing angle. High frequency converters are either voltage or current source converters. High frequency converters are mostly used in DC-DC, DC-AC and AC-AC converters, in which fast switching based on a pulse width modulated signal is required. So let's start with voltage source converter. When we are talking about voltage source converter, that means the input source is a voltage type. So basically using a capacitor we can store energy, and this capacitor can provide voltage source for this converter. And normally for voltage source converter we have inductive and resistive load. In this case we actually chop the DC voltage, and based on a pulse pattern we generate this voltage at high voltage, this type of voltage waveform at high voltage, high current, the output of the converter suitable for high power system. And when we are talking about current source converter, that means the source is a current source, the input source is a current source, and normally we can have a large inductor, and if the current through the inductor is continuous, then we can consider it as a current source. So that means this inverter look at the source as a current source, and then by turning on and turning off the switches here in the converter we can chop the input current and then provide pulse pattern at the output of the converter suitable for basically resistive and capacitive loads. In some complex power processing systems, the instantaneous input power is not equal to the instantaneous output power. The reason is that we need to have different conversions in order to achieve robustness and to design a reliable power converter. So that means if we look at the input power, so at any time input power is not equal to output power, but the average should be if there is a lossless system. So let's look at the switching converter in this topology. So basically, as an example, if an input source is the grid voltage and a demand is to deliver an adjustable DC voltage to a load, so we need to convert the AC voltage into DC type through a first converter. So that means the first converter should be AC DC converter, and the reason is that the input voltage is grid voltage. So what we get here, we get DC voltage. If we have a capacitor here, basically the voltage across the capacitor is almost like this voltage waveform, but that voltage is not suitable for different applications. So now we need to have another converter. So that means here we have a DC voltage. So this source is a DC source for this converter. So we need to have another converter which is DC to DC. And what's happened here, by controlling this converter, we can adjust output voltage. So in this case we have two converters. The first one is AC DC converter, and the second one is DC DC converter, and these converters are connected through this capacitor, and this capacitor is a filter for this converter and is the voltage source for this converter. Another example is a two-stage conversion process where the first one is a diode rectifier. So the first converter is a diode rectifier. That means if the input voltage is grid voltage, so we have AC to DC converter, and that means the input voltage, magnitude and frequency are constant because this is grid voltage, and what we get across the capacitor is unregulated DC voltage. And now for some application like motor drive, we need to control the output frequency, and we know when we need to control the output magnitude. So using this converter, which is basically DC to AC converter, we have DC voltage. The voltage across the capacitor comes from this converter. So here we have unregulated voltage, but using this converter, and based on pulse width modulation technique, we can control the output voltage and frequency and provide variable frequency, variable voltage for different applications like motor drive.